Eu da.
Eu, Andron. E lucrarea cu Khan Communication Solution Design based on Open Source Development Platform.
Eu voiam să vă întreb dacă nu mai bine continuăm, că nu mai aveam, ca să nu mai ocupăm spațiu, să mai încep eu prezentarea de la zero. Cum... Nu, a căzut net. Da, acum să dau, am dat share, da? Ok. Let's continue. So the idea of these simulations are to find out what happened in the early universe. As I told you before, we don't know because our telescopes cannot see that far in the universe, therefore that far in the past. There is no technology to do that right now. That's why we do simulations for different scenarios, and then we let them evolve for 13 billion years and then compare the results of the simulation with what we observe today. That is the basic idea behind it. In order to start the simulation, I needed to know how the current black holes are, what is the distribution of the black holes right now. Therefore, I did a catalog of black holes and calculated their mass in order to see the mass function, because that was an important factor. If I have the mass function, I know how many black holes, how they are relatively positioned in the universe right now, and therefore when I construct the simulation and I get some results, I can compare the current distribution with my distribution from the simulation, and that means that the scenario that I built in the simulation is confirmed or not, depending on the result. How did I create that catalog? It's very simple. In the previous image, you could see a galaxy. In the center of the galaxy, there is a massive or supermassive black hole, and the mass of the black hole is directly related to what is in the vicinity of the black hole. So there are some relations that connect the mass of the black hole with the luminosity flux. So you have here the F in 2 microns. That's a luminosity specific to the vicinity of the black hole and the distance to that galaxy that has the black hole in the center. So this is a proportionality. We have to transform it into an equation. It's very simple. I used about 600 black holes, masses of black holes that are already confirmed in the scientific literature, and extracted this proportionality factor in order to make it an equation. After I extracted the coefficients, I built my own catalog. Basically, I would go the inverse process. Instead of finding out the coefficient, I would have the coefficient, the luminosity flux, and the distance that I could find in catalogs with data that exist right now, and then calculate the potential black hole that is situated in the center of the galaxy. And I constructed a catalog about 8,600 masses with a high level of confidence. The previous catalogs were somewhere around 2,000, 3,000 masses, so this is a high increase. And I'm talking about black holes that have a mass of 10 to the 8 and 10 to the 9 solar mass, so supermassive black holes. The massive ones are between 10 to the 5 and 10 to the 7, let's say 10 to the 6. And the simulations were based on this mass function, and again I had to construct this framework using a code package named Gizmo. This Gizmo code package is very used in astrophysics. It's an n-body simulator. It's written in C, but for the initial conditions, when you start a simulation and use the functions that are already in the code package, you can write it in any language. So I used Python in my case. And the purpose to grow the black holes that I have in my initial conditions to 10 to the 8 solar masses, and to have them in concentrations between these values, 350, 2000, 2200 black holes per kiloparsec cube. Because this is the distribution that I got from my catalogs that was confirmed. It was already, it's the same mass function that was already published in other articles. So the mass function stays the same. I use it, and the results of the simulation will be compared to that. Now, when I start doing a simulation, I basically I have an initial volume of black holes. You can see here the black holes with the blue dots, and the red particles are gas. This is gas for the black hole in order for the black hole to grow. You have two main popular methods, accretion and co-merging. So accretion is when the black hole eats the gas around or in the vicinity, and merging is what merging means, the two black holes that merge into a bigger object. And I do this, I initiate a volume with seed black holes, so initial black holes that are either very small or relatively big, and then I let it evolve for 13 billion years until I get the current distribution that I can compare with the observational results. And of course, you can see here, depending on the initial conditions, I get different behaviors in time. The scenarios were three types. So I can have heavy seeds that's relatively big, like 10 to the 5 solar masses. There are scenarios that I presented at the beginning where you could come up with black holes like this when they grow inside a supermassive star or direct collapse of the gas. And this is one of the cases that was confirmed because the results of my simulations were right between the values of the interval of the current predicament. So for the heavy seeds, that's pretty easy because they're already a little bit bigger. But for the lower seeds, that's 10 to the 2, 10 to the 3 solar masses, that's very hard. I couldn't even grow them to 10 to the 8 solar masses, which was the first condition. Before verifying the concentration. And then I also use the hybrid scenario where I have low seeds and bigger masses, heavier seeds. I could obtain black holes with 10 to the 8 solar masses, but their concentrations were way too low compared to the interval that I was searching for. So 10 to the minus black holes per kiloparsec cube compared to a few hundred to a couple of thousands. And these are the general parameters. As I said before, I integrate my code for 13 billion years. I start with an initial number of black holes of 4,000, and then I add gas particles in order to have a cloud of gas for the black hole to eat. The important result is that, one of the important results is that I obtained a merging rate behavior. Merging rate is very important for the future space observatories of gravitational waves, because as I told you, black holes, when they merge, they create these gravitational waves that cannot be stopped by electromagnetic phenomena or lumps of gas. These are gravitational effects that are undisturbed until we detect them. So we can investigate different phenomena in space without being afraid that the information will lose on the way to our telescopes. So there are observatories for gravitational waves. This is a force that we do not understand yet. And one of the main topics right now when they're building it, because it's built by engineers in Florida right now, is how many events can it detect? Is it 1? Is it 2? Is it 1,000 per year? We have no idea. This is something that is studied right now. So if I have a merging rate between the black holes, that means that I can expect a number of events per year. and then I can optimize my engineering pipeline or my devices, my tools that I will use in order to detect them. And in my case, it is somewhere around a few tens to 1,000 events per year, which is in agreement with other articles. But what is more than the current articles is that an article right now tells you one value of merging rate that we can observe right now. I have a behavior, so I can go back in time and I can say that when going back in time, there was a different kind of merger rate. So this is the novelty of this activity and this work. And I wanted also to tell you about other methods of growing the black holes, because as I told you, the most popular ones are accretion, when they eat the material around the black hole, and merging. But I'm starting to focus on a more exotic one. I have a picture right here in order to explain it better. If a star approaches the black hole, half of its material is thrown into space. So the black hole does not eat in a very organized way. It's actually very inefficient. Half of this mass actually gets bound to the black hole and gets eaten, but half is thrown into space. And this is basic accretion. But there is a situation where this star, when it approaches the black hole, so you can see here there is an area with green. This is the area where the star becomes disrupted. It could, the atoms of this star become rows of spaghettification, which is the official scientific term. And when it gets to the area with the black part, which is the event horizon, where nothing escapes anymore, then it gets eaten completely. So there is a space between the green line and the black area where this star can be in millions of years disrupted in atoms, basically. And that's what we can see with the normal telescopes, because this emits light. But this is the classic accretion process. But if you have a black hole that is a little bit bigger, that means that the black area right here will be also bigger. So you have an area where the star enters the gravitational influence of the black hole, and the black area where there is no way to come back from for the material. So if we have the black hole a little bit bigger, that black area becomes bigger as well, and it overlaps the one with the gravitational influence where the accretion would happen. So if a star comes in the second case on the right, it would just get eaten completely. There is no more half of mass going into space. It's a very efficient process, and this term was actually named by me and my team, star gulping, and this is an exotic way for the black hole to grow, very efficient. But the black hole has to be a little bit bigger. So I'm trying to integrate this into my simulations as a third method of black hole growth. And if it ever becomes famous, that will be really nice, because the term was coined here in Romania. Just to keep my presentation short, I did a catalog of masses of massive black holes. I validated a scenario which involves initial seeds, initial black holes that are relatively bigger, that you can obtain in theoretical scenarios that we cannot observe right now. And I obtain a massive black hole merger rate with a behavior of that merger rate, and I'm continuing with adding different growth methods to my simulations. And of course, there's some perspectives like publishing the catalogs and tweaking the simulations, because right now the simulations start from initial volume, they expand, and then the results are extrapolated. But in a real universe scenario, that is not the case. But we cannot simulate even on supercomputers a whole universe, so you have to start from a lower volume. But you can also add different optimizations, like external forces, like my population of black holes could interact with another population, and other things like that. And there's also other characteristics that can be extracted from these results that tend to be very important in the astrophysics field right now. because we're going into space when discovering this, observing these gravitational waves, which were observed only on Earth before. So there's a lot of work here. So thank you.
Okay, thank you for presentation. If it's some question, please. No? So thank you very much. And
Thank you.
now we go to Mrs. Flavia Andron.